Hi, this is the third lecture on advanced nonlinear physics. It deals with viscous shocks. So it's the following of the previous one, of course, and it's a short lecture because the main part of this lecture will be dealing with the solution of the first tutorial and will be broadcasted using different support you see on the website. So let me just remember what is all this about. So one wishes to solve again the same equation. This is what the so-called Cauchy problem. One wants to determine rho of xt knowing an initial distribution rho naught. So we saw last time indeed that when characteristics cross, wave breaking occurs and a shock is formed, and with the position s of t and the velocity ds dt, or in short s dot, is q plus minus q minus divided by rho plus minus rho minus. And these notations are defined in this sketch here. So this is rho of x and t. The continuous line is the solution one would obtain by means of the method of characteristics, and one imposes a discontinuity here at position s of t, which is the position of the shock. One calls rho minus, which is rho of s minus, so just at the left, and rho plus, which is rho just at the right. And same for q plus and q minus. And we saw last time by imposing flux conservation that the velocity is given by formula 1. It can be understood as indeed resulting from flux conservation by writing q plus equals, simply q minus plus s dot times difference of density. So just look at this picture. You have an interface that moves at velocity s dot, and at the right you have density rho minus and flux q minus, and at the left, and at the right everything is with superscript plus. So here, for instance, rho minus and rho plus. Okay, and the velocity of the shock is there. So you see, indeed, the outgoing flux at the right is the incoming flux plus the motion of the shock times the difference in density. So maybe this is a simpler way, maybe more physical to understand than the way that was used in the previous lecture, which was more mathematically to establish this formula for S plus. Anyway, that's what it is. And now we go back to the Riemann problem. So consider, for instance, a case where C is an increasing function of the density. So here we have a Riemann initial condition with density ρ1 at the left and ρ2 at the right. And one denote by C1, C of ρ1, and C2, C of ρ2. So this is not the case for an increasing function of ρ. This is not the case for traffic flow, but well, consider this case. So the method of characteristics tells us, we saw that already, that this guy, red line, corresponds to a motion with velocity c1, and the limiting case is just at point 0 here. This x equals c1t. In the domain x positive, the velocity is c2, so one has characteristics which are straight lines of velocity c2, and the limiting case here is here, x equals c2t. So indeed, here one has a shock since characteristics cross. And the solution is simple. That's here. So one draws, one draws the motion of the shock with here s plus, which is a constant given by formula 1. And this delimitates the two regions. At the left, one will have density ρ1, and at the right, density ρ2, and something like that. So ρ1 until the shock, which moves here at constant velocity s dot, and then density ρ2. So the green line is the initial distribution. Here, this is the distribution at time t. So one does not go up to C1t, which will be the position expected earlier there. One stop at s dot t, and okay, and that's it. Just a remark. C is not always a monotonous function of density, and one has to check indeed something very sensible, that S dot is between C2 and C1, and this is called lax entropy condition. And if you're curious about that, you may check on exam 2019 to 2020, when there is an exercise dedicated to the study of what happens to the shock when C is not monotonous. Just a final remark here. The initial profile is schematic with no characteristic length, and this means profile at time t also has no characteristic length either. It is a self-similar, so one can plot everything as a function of x of t, x divided by t, and then this remains constant. It doesn't, I mean, this guy does no longer depend on t. Okay, so as an exercise, a very simple one, consider the following. Let's try to describe the motion of the trailing end of a traffic jam. So this is the traffic jam here. No cars for X positive are stopped, and they have the density ρj. Okay, remember this is C of rho, and for the traffic flow, it looks this way. Okay, at ρj, one has no flux. Cars are bumper to bumper that touch one the next one the other. And here one has a flux of incoming cars with density rho in and corresponding flux q in. With, for instance, in this case, rho in is smaller than rho m. Rho m is the point where C changes sign. So one will have a shock, of course, because these guys there at the left, they move with velocity C in. So it means this curve has a slope 1 over C in. And these cars, not the cars actually, and it's important to say that it's not the cars, but this is the motion of a perturbation of density. And here, the perturbation of density move backward with negative slope, and it's 1 over Cj. 1 over C because I plot t as a function of x and not the opposite. So here one has a negative slope. Indeed, the characteristic would tend to overlap. And this means when we have a shock, and the shock velocity is computed by means of for this formula 1 in the first slide, which gives here S dot equals Q of rho j, which is 0, minus Q in, divided by rho j minus rho in. And this guy is a constant because everything there is constant. So the shock has a constant velocity. We will see in the tutorial examples where the shock doesn't has a constant velocity because some of the rho are time dependent, but it's not the case here. So it's a simple situation. And the density looks like that at time t, okay? Of course, cars don't move, but the perturbation of density moves backwards because S dot is negative, and this is what one expects. Cars arrive and pile up at the end of the jam. One way to understand this formula, again, is to derive it very simply as follows. One says during dt, the number of incoming cars are incoming flux q in times dt, and they arrive and pile up with an increase of, they arrive at density rho in, and they pile up with an increase of density rho j minus rho in. Here, the difference, rho j minus rho. So one will have number of cars q in dt equals rho j minus rho in times the dx, which is the dx is the motion of the shock, and its absolute value here. And the absolute value is, since s dot is negative, is minus s dot dt. And combining these two yields the blue formula here. It's again a different manner to see things, maybe more physical than the more mathematical way used in the previous lecture. And this is the end of this short lecture. The rest will be, we will be in the rest, we will be occupied. Let me try to stop recording. I can't.